Welcome to the first mini-lecture for Module 10 on correlation and regression. In this mini-lecture, you should be able to differentiate between positive and negative correlation, calculate and interpret Pearson and Spearman correlations, interpret the appearance and fit of a regression line, understand R and R squared, and recognize assumptions required for correlation and linear regression. This module is just going to do a general overview to these ideas. So in univariate statistics, which is what you've been covering so far in the class, we have examples where we have one variable with multiple levels. These levels define our groups, and then we test for significant differences among groups. And some examples of these univariate statistics include t-tests, so a one-sample t-test, independent sample t-tests, and the non-parametric equivalent, and also paired sample t-tests, or an ANOVA. So a typical question we would ask in a univariate statistical approach is, does experimental drug X produce some significant health benefits? And in an experiment, we could apply a drug versus a placebo and do a t-test to see if there's a mean difference between those groups. Or we could apply different doses, so we could have a high dose, a low dose, and then no dose, and do an ANOVA to test to see if there's some differences between those groups. So that's a univariate statistic where we would have an experimental treatment of drug, and then our treatments would actually be if there's a drug or no drug, for the example of a t-test. And that's univariate statistics. And this is different from bivariate statistics. And in bivariate statistics, there's two sort of generally related methods. So one of these is correlation, where we're examining the association between two variables. So we're seeing how two variables are related to one another, two continuous variables. In a regression, now we have two different variables, but we want to make predictions about one variable as a function of another one, using the equation of a straight line. Of course, we're going to go through all of this, and first we're going to go through correlation. So what is a correlation? You've heard this word correlated used a lot, but it actually has a specific statistical meaning. And the way that you often hear the word correlated used in everyday speak is something like poor health is correlated with pollution, or obesity is correlated with poor diet. But when we think about what does correlated actually mean, we're thinking about how are these variables related and how strong is the relationship. So if poor health is correlated with pollution, well, we would expect if there's more pollution, people would be in worse health. But how strong is that relationship? And a correlation is a statistical method for examining the association between two variables, and we're doing this in a quantitative manner. When we look at bivariate distributions of data, we have data comprised of a pair. So we were going to have a value for x that would go along our x-axis and a value for y that would go along a y-axis. And these are continuous data scores, and they're paired for individuals that are measured. So with the example of poor health correlated with pollution, we would have information for an individual and the level of pollution they experience, and then we would also have a measure for their health. So one example could be in paleontology, they could have bone lengths of specimens, and they collect data on fossils of femur and humerus lengths, and each data point can be plotted from the same specimen. And we call this a scatter plot. So this is an example of a scatter plot. Each of these data points comes from one individual, where we have a measurement for femur length and for humerus length. So there's a logical pairing for each of these points. So recognize how this is different from when we have t-test examples or ANOVAs, where we have some categories or treatments, and then we have some response variable that we've measured. In this case, for a correlation, when we have bivariate data, we have femur length and humerus length, and we're seeing how strong is the association between the two of them. So we have different types of correlations. They can be positive or they can be negative. So if we have a positive correlation, it'll look like the plot here. So we have our x-axis and our y-axis, and a positive correlation, the variables are increasing together. So as x gets larger values, y is also obtaining larger values. A negative correlation is where we would have an increase in x and a decrease in our value of y. Or we can have a scenario where we have no correlation at all. So as we increase our level of X, so we could be increasing our levels of pollution. If there's no effect on health at all, we would expect the plot on the far right. And when we look at a correlation coefficient, the product moment or Pearson correlation coefficient is what we call R, provides a quantitative measure of the strength and type of association between two continuous variables. This is going to range from -1 to +1, so we have a perfect negative correlation to a perfect positive correlation, and a value of the correlation coefficient of 0 means that the two variables are not correlated at all, so there's no relationship. So let's look at some plots of what this would look like. Here we have on the left-hand side, we have a correlation coefficient of 0.7. You can see that it's also positive, so as we increase our values of X, our values of Y are also increasing, and that the scatter of our plots is not too far off that line, so it's going to be a value of 0.7. In the center panel, it has a value of 0.3, so the slope here is the same, but there's more scatter in the points, so that association is not as strong. So we're going to have a little bit of a weaker correlation, and then on the right-hand side, there's no relationship at all. So as we increase our values of X, there's no influence on Y. It's not trending as an increase or as a decrease, so that has a correlation of 0. So the closer the points cluster together around that line, the stronger our value of R will be. This is just now showing that we can have positive and negative values, and those are just whether or not it's a positive or a negative relationship. The actual value, so of 0.7, is how tightly those data points are clustering around this trend line that could go between them. With Pearson correlation, we have some assumptions, including that our study participants are independent random samples from the population, that the relationship between X and Y must be linear. So in your textbook, it shows some examples where it's not linear, but to do a Pearson correlation and to look at the correlation coefficient R, it has to be linear. The two measurements have to be on an interval or a ratio scale of measurement. So they're continuous scales, not categorical. The two measures are normally distributed. We have no influential outliers, so when we look at this graph in the corner, on the left-hand side we have a correlation coefficient value of 0.4, but we have this outlier that's circled that's really drawing the line and pulling it so that it doesn't fit the other data points very well. So it's on the end, so it's really pulling it down on the right-hand side. But if we get rid of that outlier, we have a much better fit to the data, and our correlation coefficient is now 0.7. Another assumption is of equal variance, called homoscedasticity. And in this plot you can see as we move from low values of X to higher values of X, that the spread in those data points is consistent. So if we drew a line through that, with the increasing trend, all those data points would be quite consistent. But heteroscedasticity is on the right-hand side, and that means unequal variance, so that the data are more tightly packed together with lower values of X, and as we get to larger values of X, that spread really increases, and so that violates some of our assumptions. You could do something, for instance, like it's called transforming the data, where you would take the log of those data points, and then that should get you back to homoscedasticity when you have a pattern like you see there. One very important thing to note is that correlation is not causation. So here, you know, if everybody who went to the moon has eaten chicken, if you eat chicken, that's going to make you go to the moon. Well, that's just ridiculous. So correlation is not causation. Some people might say, well, you know, there's more cases of autism, and this is related to organic food sales. You know, and the correlation coefficient that is here, so this is looking at data over time, but if you look at how autism and organic food sales are related, well, it has a really high value of R. But again, does that mean that one thing is causing something else? So there's more organic food for sale, so that's autism, or the opposite way? That doesn't make any sense. So again, correlation is not causation. And you can come up with all sorts of things that are correlated but do not actually mean that one thing is causing something else. So here we have fresh lemons imported to the U.S. from Mexico, and total U.S. highway fatality rates. So if we import more fresh lemons from Mexico, then this would suggest, if we were thinking about causation, that fatality rates on the highways would go down, which of course, again, doesn't make any sense. This value of r squared up in the corner, we're going to get to that when we end up talking about regression in a different mini lecture.